guess I'll just leave that going on my phone so I can take a look. Probably be very distracting, but yeah, research hour. It's just meant to be some time to mess around, pull open some tools, talk about projects. It's pretty open format. It can be meant as, I mean, if you've got questions and you're the only one who shows up, then hey, looks like that's a one-on-one, and I'll answer your questions as best I can. So, yeah, we're just messing around, really. We can talk about your projects, talk about my projects, talk about things we want to do 3 weeks from now. It's all fair game to me. But, so, I guess we'll kick this off. If it's going to be my research, then there's one thing that I really need to get done, and that is find an H-bridge driver for Project Darwin, which I've been teasing on Twitter for those who watch on Twitter. I'm gonna casually drop that link in chat. Feel free to follow me over on Twitter if you want to get notifications and just my general mental word vomit when I'm working on projects too late at night and I get frustrated. So that's kind of what's on there. But yeah, we need to find an H-bridge driver because for Project Darwin, we're going to want an isolated half H-bridge driver, which needs to have a charge pump inside that can manage to have enough current coming out to drive the gate of the MOSFET at 100 kilohertz. So I was doing some tests with an LT spice, or an LT part, apart from LT, and they spec it up to like 100, no, yeah, I don't know, like a couple hundred megahertz. I have no clue why, because it can't get even close to 100 megahertz. Let me pull up the simulation I have. So, yeah, this LT1158. That data sheet, ridiculous. Sorry about that. Just servicing chat. Not quite used to hopping in there. More new things. But yeah, so there's this H-bridge driver that I've been trying to simulate to make sure it can actually run. And if I find DC supply current, yeah. So here they're like, if you're running at 10 kilohertz, it'll take 10 milliamps, and then you go up, and then at 100 kilohertz, it's like, oh, yeah, we can drive 1,000 picofarads, no problem. 10,000 picofarads, no problem. In my simulation, I'd drive it up to 11 kilohertz, and it would just break down and stop. It just wouldn't drive the high side FET high anymore. It didn't have enough in the charge pump, and I'm like, well, then why did you spec it to 100 kilohertz? And I'm sure there's reasons. Maybe it's mostly marketing reasons, but I'm sure there's reasons. So we need to find one that won't break down at 100 kilohertz. Oh. Yeah, so what this is here is I've got a simulation that I made, and this was one that uses that less than ideal driver that I can only push to 10 kilohertz. And this is me doing a step response to see how bad the comparator and op-amp control loop is. Project Darwin, we're actually going to tune a PID, well, a set of PID control loops and digital filters, and stitch that together, run it in real time on a micro, which, yeah, that's been kind of a pain. Getting that to run real time in a micro? No thanks. No thanks. Yeah. But at any rate, so it's just running the step response. Yeah. So while that's going, yeah. That's not too bad. So this is showing two things. It's showing the reference voltage as well as what's happening in real time. No, that can't be what that is. That's what it was supposed to be showing. VREF. There we go. Need to multiply that by 20. All right. So now you can see there's the step impulse. We said turn on at 16 milliseconds. Then it went and thought about its life for a while and then went kind of crazy. Which, what that is probably phase shift in my controller that I'm not compensating for. Otherwise, could be hitting a bandwidth limit on these op amps. There's phase shift from this last filtering stage that kind of makes it break down. The RMS value is fine, but I mean, it's like 2 volts of ripple. I don't know what percentage that is, but a lot. In the final implementation we're trying to get like 0.1, 0.2, 1% ripple or something. And yeah, it's just not gonna happen. Not gonna happen with this controller. But just to make sure that everything's working right, because we're implementing analog filters in discrete time because, well, I'm much better at designing analog filters than digital, and I have a digital microcontroller that can make my PWM. Yeah, I suppose I could use comparators or op-amps to build all of the filter blocks, but the main issue is that I'm using this to drive some power electronics, so there's going to be a lot more distortion and noise than there would normally be, and because of that, the analog control would need to be like shielded, need to be like in a box, and need to have like at least 4 layers on the PCB, probably more, so I could basically put every critical trace in a diff pair shielded with ground all around it. Or we just use a microcontroller and the nets and nodes are so small that no significant energy can couple into the microcontroller and it's just fine. So yeah, I just had to kind of bite the bullet on this one. Trying out a new type of processor. And it's the STM32. It is this. Well, I can't find the specific one, but basically, it's one of these dev kits from ST Micro. They have this whole suite of parts, just tons and tons and tons of different dev kits, with many different pin counts, peripheral counts, and they have this wonderful tool called the STM Cube. Basically, you go in there and it'll actually help you select a microcontroller to meet your application, which is pretty cool. And then once you're done, it'll, in theory, compile code that is, in theory, useful, and that you can, in theory, interface easily with to start up your peripherals. Not that I'm salty about anything. Definitely nothing to read into there. But that was just a joke. I had an awful experience with it yesterday. I just couldn't get the darn thing to work. It's just, they have this great hardware configuration tool that generates code that interfaces with a bunch of libraries, all developed by ST. And then ST has software libraries, which they have written, and it's extensive hardware abstraction layer code, which is just really convenient for most people to work with. But once you get that HAL working, I keep getting distracted by seeing myself from 10 seconds ago in the stream. Oh man, it's driving me crazy. I need to like hide that pain so all I can see is chat. Oh, I wonder if there's a way I can do that. That'd be awesome, because I cannot stand seeing that. Oh. Settings? Full screen chat? What do you want from me? Oh no, now I can't see chat. Oh geez. Why did I click anything? Oh, got it. Oh. Yeah. So this is STM Cube. And it'll help you. You can pick how much RAM you need. You can pick, what in the world? You can pick how much RAM you need, what frequency you want to run at. It's pretty incredible how much I/O you need. And then as you go through and put in all these filters, it'll tell you, hey, here are the microcontrollers that meet your needs, which is really awesome, because this tool will help you by compiling that lower level code. Not to mention it gives you pricing information for all of these, which is amazing. So let's say I wanted something for a development environment, and I want to have a really strong, powerful processor to get the code up and running, just something that's completely overkill. But then 3 months from now, I want to switch it back to something that's a little more reasonable, something that'll be, you know, profitable, a reasonable pick for an end solution. Well, then you just pare it down to the amount of RAM, the amount of flash, the amount of I/O that you really need for your application, and you can pick the cheapest one. So, yeah, that's something that I've struggled with in pretty much all of my projects in the past, is like, you know, if you need to switch to a different processor, a different I/O count, how do you even know? How do you even know what to pick? Right? It's such a crazy thing. How do you know what you're going to need a month from now? So you can go in here, configure all your clocks, configure all your timers, you know, and then in theory, once you've set this all up, your ADC will trigger when you told it to when timer 4 overflows, and then yeah, it just doesn't. But in theory, really convenient. And yeah, so I just got this working last night way too late, and this is just testing out the PWM capability of the device. Just got a value counting up, then it updates the PWM value once every 10 milliseconds, I think. Yeah, pretty neat. Well, I'm running out of creative things to talk about, so I think I might just need to default to some of that research I was talking about. I can only be entertaining for so long if I got nothing done. Yeah. taking a look at chat. Nothing happening. So if you want something to happen, hey, you should put something in chat. I'm staring at it right now. Any sort of questions? Yeah. You can quiz me if you like. I might not answer if I realize you're just quizzing me, but you can. Coffee's good. So this gate driver we're looking for, I'm not really sure how to guarantee that the device will meet its specs other than grabbing something from TI instead of from ST. I'd say I'm a little biased, and that'd be true, but I'm only biased because every part that I've ever bought from TI has been fully compliant with its datasheet. So it's kind of like they tell you what they're going to do, they do it, and then it does it. It's pretty straightforward. So we need to, high side voltage. Need a pretty high one. I've been kind of a jerk about Project Darwin, that whole project. Just because I don't want to give it all away, right? This is going to be a huge project. We technically haven't kicked it off yet, but I need to get some legwork done before we kick it off proper if I want to have any chance of getting a video a week out. There's a lot to do. My to-do list of things to do to make sure that we can actually do the project is about 20 things long right now, and I want to get like 12 of those done by the end of the week. So probably there'll be some enraged random comments on Twitter, but yeah, that's okay. I've been kind of silent from Twitter anyway. I like to post something every week or two, but just didn't get around to it. Oh, I'm not sharing my screen with you. A mistake. Sorry about that. Probably makes a lot more sense when you can see what I'm looking at. Yeah, so we're looking at these half H-bridge drivers, and I would like them to drive N-channel MOSFETs. And we want synchronous, which means that it won't let you have shoot through. That's what that means. Synchronous means your high side and low side should be synchronized and not just independent control allowing you to clamp V plus to ground, which in my opinion is not necessarily the it's not great. A few kiloamps flowing for a brief fraction of a second and then nothing. So, I don't want to have to deal with the no lead part. Just not in the mood. So it looks like we're going for the 8SOIC or the 10. There you go. We've got some great looking parts. As far as I can tell, they're all equivalent. Source sync, 118 volts on the high side. But you know what? Get rid of that. Yeah, there's not. Interesting. This is going to provide an interesting challenge when we get to the final implementation, because How do I zoom in for you? Do I just do this? I think I just do that. So right now, the highest voltage is 118 volts. And the issue with that is that the final implementation is going to have at least 300. Oh, that's not great. And the issue is that this part's probably rated for 500 volts isolation from high side to low side, which is all right. It's all right for this application, since we're going to have an isolation boundary between the thing driving this and me, so we'll have 4 kV isolation somewhere else. Yeah, it just means we won't be able to use this part again. We'll need to find one with a higher degree of isolation. I mean, at least 500 volts, at least 400 volts for the max bootstrap voltage. That's a pain. Well, let's crack open this datasheet anyway. Let's just take a look. Well, the first one that's got a lot available. So this is exactly what I would expect to see. You've got a source voltage, got some sort of, looks like this one has an integrated diode for the bootstrap supply. (100 picofarad loads with 15 nanoseconds rise and fall time. Should be enough. Should be plenty. Some monitoring and yeah, that looks good. Looks like stream's doing okay. Let's see. So this data sheet actually shows operation above 100 kilohertz. So I'd hope that it's actually able to do it, seeing as it goes up to like 800 kilohertz. Let's see if they have a graph for frequency, PWM frequency versus gate capacitance. Actually, is this even one that takes in PWM, or is this taken two separate? Control input. Logic 1 is high side on, low side off. Logic 0, high side off, low side on. Okay. So we can drive that with PWM and we just go back and forth. Thankfully, it's got symmetrical propagation delay. Just makes life easy. You don't need to compensate for it. Here, I can zoom in a little more. What I'm trying to find in here is a graph that will give me certain belief that it will operate at 100 kilohertz. The reason why I need this to operate at 100 kilohertz is because if we don't get this to drive at 100 kilohertz, the output ripple is going to be huge because we won't be able to buy an output inductor with a high enough value to filter the PWM switching. So I need to know that we're able to drive that H-bridge fast enough. Yeah. I love controllers with integrated shoot-through protection. Like, when it works, you just don't need to worry about it. And when it doesn't work, you just say, well, never going to use a part from that vendor again. Then you find one with programmable dead time. Yeah, this is right here. This is what we're going to be building. And there'll be two of them. And I want to have one PWM controller running both algorithms if I can. But yeah, right here. This is what we're going for. Output filter stage, just basic. It's an LC filter stage. I think that would make it second order. It's been such a long time since I did control systems and filters. I really need to brush up on that. It's on my list of things to do this week. But at any rate, the output low-pass filter, which will block the 100 kilohertz and allow the steady-state DC through, the bootstrap capacitor with the diode for boosting the voltage. Could be switch capacitor. Not really sure what kind of supply they've implemented in there, but yeah. Design requirements. Hey, beautiful. Oh, typical application with math. This is why I love TI datasheets. Like, here, we're going to walk through all of the math and tell you what all of our values are going to be for every component in our typical application schematic. Wow! That is a lot of work. Like, this right here, what we're looking at. This is the difference between the kludgy nonsense I've been beating my head against the wall to get through for the last 2 days and a properly documented system. Now, I know that with like the HAL and the micro, there's a lot more pieces, but this right here, for like using their HAL to set up PWM, using their HAL to set up an ISR for general 1 kilohertz timing, linking a ADC channel to a PWM channel. Like, they have the HAL to make it hardware abstracted, like that's the point. I just need to know which commands are relevant to each function of the micro. And when I'm trying to just get a list of commands that are useful for those types of things, there's like 15 different like YouTube videos, articles, whatever, none of them from ST. And it just, like, tell me how to put the blocks together. They're just like, here are these blocks, here are these tools, figure it out. Which, I've been getting through it. It's just tedious and frustrating, and it doesn't need to be that hard, because there is someone at that company that could explain how to do what I want to do in about 10 minutes. If I were sitting at his desk and he was given the time of day to talk to me, 10 minutes. I bet we could have this micro running, doing exactly what I needed to, at the exact frequencies I needed to. Because all it is right, here they tell you I'm doing 200 kilohertz. Here's my maximum gate charge. Here's my supply voltage. They just walk you through every piece of the puzzle And I bet they'll explain the limits of all of these parameters. That's exactly what we need. Because if we want 100 kilohertz instead of 200 kilohertz, yeah, we'll need to modify the output filter. Yeah, we might need to change some small things about their application, but I mean, it'll be 80% there. It'll be 80% correct. So I'm going to take a look at this. I'm going to take a look at this specific driver from TI. I like it, but I might need to search for an alternative that has better isolation so that we'd have a fighting chance of using it on both the proof of concept and the future phases. But this looks good. It looks like this controller actually supports 100 kilohertz. And honestly, pushing above 100 kilohertz, there's no point. The micro I have, not a chance. It wouldn't stand a chance. I think I have like 78 steps between 0 and 100% duty cycle at 100 kilohertz. Like that's the most I can get because I'm driving that PWM module as fast as I can with no pre-scalers. It's 80 megahertz clock coming in, no downscaling. So you got a 100 megahertz clock going to that PWM chip, or the timer module. And yep, so I'm counting 16 bits worth of numbers from start to stop at as fast as I can count. And I have to trim it back to like 79 to get 100 kilohertz. Yep, and maybe we'll have to just pick a higher clocked processor. That might be what it comes down to. Now I gotta refresh my coffee. I'll be right back. Yeah, it's amazing what happens when you stop for coffee. Just, sit back, think about life, really appreciate things, and I can't really see who's watching. I can just see how many people are watching. And that number's 2. And I've got my phone open watching the stream, and I've got the preview window watching the stream. So I wonder if I am both of the 2 people. Oh, that'd be awesome. There are 2 people watching your stream. You and you. Yeah, it doesn't matter. There's an archive. I can upload it later. Dying. It's great. I forget what I was talking about. Something about this controller. I don't know. I've got fresh coffee. So, with this H-bridge, the tricky thing about it is that if you have an N MOSFET and a P MOSFET, or like an NPN or PNP transistor. Doesn't really matter. Let me grab LT Spice. We'll mess around. I'll use this as a way to demonstrate. So if we have a PNP transistor and we have an NPN transistor, it's really easy to drive these in an H-bridge configuration because this node here, how How do I get a bigger cursor? Not sure. But at any rate, the base right here. Oh, wait a minute. My display settings are all screwed up. Oh, come on. One moment, please. Please wait. I need to increase the width of the traces so you can actually see them. Ugh, I had this all set up, then it updated. Control panel, waveforms. Yep. There we go. Okay, so now we just need that for drawing options. Hey, there we go. You can see that a lot better. Okay, so now on the base here, this wants to be tied to ground to turn on, which is easy. It's really easy to tie that to ground. And now this one wants to be tied higher than ground, which is really easy because it's already at ground. There you go. Problem solved. And with a PMOSFET, it's a very similar situation. I believe that is that right? Is that how the arrow should be? Because this is oriented. No, whatever. Let's just assume that's right. I'm pretty sure that's right. There's something about trying to talk about something while doing it that means that you will be wrong 100% of the time. I'm just not even going to try. So with a PMOSFET and an NMOSFET, it'd be the same thing. You want to tie this lower than that pin, and here you want to tie this higher than that pin, both of which are really easy with one catch. The PMOSFET will not have symmetrical turn-on or on-state resistance as the NMOSFET, so it won't be symmetrical, and it'll be all garbage. So the workaround is, well, if you want them to be symmetrical and you want them to be paired, then just use two NMOSFETs. Use literally the same NMOSFET. That won't be an issue anymore. So, whoop, there you go. Got an NMOSFET. Two NMOSFETs. This is great. We're going to put 500 volts up here, and we're going to drive our H-bridge. Sounds good, except for if we want this to be 500 volts, that means we need 510 here. That's just a pain. You need to generate 510 volts. You need like a couple milliamps sometimes. It's no good. It's no good. And that is why we're using the H-bridge driver, because it has an integrated circuit to boost up its supply voltage to above this rail voltage. So it'll monitor this net here, and it'll make sure that it's boosting up, charging a capacitor to be a higher voltage than what this FET will need to turn on. And then when it's time to turn it on, it just dumps that energy stored in the high voltage capacitor and just turns it on. In the case of this chip we're looking at here, I think it was a couple nanoseconds, couple microseconds. Picoseconds? I think it was picoseconds. Incredible. Incredible. So, yeah, for those wondering why we aren't doing a PMOSFET and NMOSFET, it's because if we would do that, it would have a higher on-state resistance on the high side switch, which is bad because the high side and low side switch wouldn't be symmetrical, and it's also bad because we'll be dissipating more power than we need to. Both of which are not what we want to do. We want to dissipate the least amount of energy and the maximum, and have the maximum efficiency. And it's really because we have no choice. For the plant light project, whatever. If it's not efficient, who cares if it's efficient, right? There's 30 watts coming into the system. If it's not efficient, it gets a little hot. All right, sure, gets a little warm. Put a heat sink on it, right? But now we're talking about like 1.2 kilowatts. We're talking about like 10, 12 amps going through that N MOSFET. So when you double your power dissipation, you go from like, instead of going from cool to warm, like with the plant light project, we're going from like about the maximum temperature of the FET to exploding. Like the stakes are a little higher. We need to optimize the efficiency of the system, not because we want to, but because if we don't, it'll burn itself. It'll just self-destruct when we try to use it. I might not notice until I actually hit peak load because I haven't figured out how I'm going to test this thing at a kilowatt output, which, you can see the smile on my face. The fact that I need to is great. I don't know how I'm going to do it yet, but when I do, I'm going to have like a party or something, invite people over. That'd be good, just for the moment when I plug it in. It'll be a while from now. The first test is going to be lower voltage, lower current, so it's safer for me to work with, and I don't blow up a bunch of microcontrollers. Yeah. But the final implementation will, 300 volts, not 500. So it's like 310, which I guess is a little better, but yeah, it's not 500 volts, but 300 and somewhere, well, as many amps as I can push through it without having big thermal issues. And actually, you know what? I'll show you something. Give me a sec. Nope. You gotta come live if you wanna get the spoilers about Project Darwin. I have been very careful to contain my excitement in my post on Twitter. I started writing a few scripts for it, just trying to get my thoughts collected. It takes me quite a while to collect my thoughts for one of these videos, but I've been really happy with how the latest ones have been turning out, so I like to think it's been working for me. So, hasn't been quite an hour, but it's kind of my research. It's what I've been doing. It's a little bit of the why. That's how I got to the topology where I'm at. There's some more detailed videos coming about specifically why we're using the H-bridge as a voltage regulator instead of, say, I don't know, like a flyback or a forward or boost or a buck. Ultimately what it came down to is that the H-bridge switch mode power supply isn't as complicated as I thought it was, and the control system is almost identical. That's what that's what the, oh, I'm distracted. I'm pulling up that LT Spice thing again. Opening up that inverter. Oh boy, those giant lines. Here it is. So with this inverter, there's two references you can use. There's the step response reference for characterization, and then there is the like dithered voltage reference. I was trying to figure out how well this control loop was working. Okay, that's driving me nuts. Drafting options, thickness maybe like 8. Gotta tone this back a little. Yeah, so you got like the resistor and all that. And I was testing out the control system, and yes, there's a lot of ripple. Yes, since this stupid LT Spice model, sorry, since this LT Spice model, it's free, right? Can't argue with the price. They do their best. Since this part claims to go up to 10 or 100 kilohertz, but can only really achieve 10, we have to run it at 10, and since the filter network is built for 100, it's not attenuating the switching noise, so there's kind of like the big ripple, which is issue of the feedback network and the closed loop control, and then there's like the little fuzziness on top of that, which is the switching noise that would be attenuated because it would be a decade higher frequency if the controller was actually working right. Not that I'm salty. Totally not salty. That's been my weekend. It's been, hey, this is just supposed to plug in and work. Or what if we didn't? What if we didn't work? But at any rate, so now here's the reference voltage. And when I did this, it was really when I knew that I was in command of this whole H-bridge regulator thing. So I'm like, that is undeniable control. And just to demonstrate, if I go ahead and change this to like 1 ohm instead, I don't know if I've got enough current for 1 ohm. If I change it to 2 ohms, pretty sure I can do 2. And rerun it again, you'll see that the closed loop control is able to compensate for the greatly increased power output and just drive it home. Just absolutely crush it. Look at that. Increase the power by a factor of whatever, still getting output regulation. Even the ripple's reduced because, well, yeah. Ripple's reduced because, I don't want to get into it now. What I do want to get into is saying, holy crap, look at how much power is coming out of here. There's VL1. Okay. We're going to multiply this by our IRL. And that'll give us the power coming out of this thing. Look at that. This whole system, peaks of 130 watts. Yes, please. Yes, please, 130 watts. And then if I plot, for example, the power dissipation of one of these FETs, that is disgusting. We can get rid of one of these. So the power dissipation in this MOSFET comes down to an average power of 5 watts. An average power of 5 watts. Think about that for a moment. So there's 5 watts of average power in this MOSFET, mostly due to switching losses, as you can see from the fact that there's a spike when it turns on and a spike when it turns off. So it's the switching losses here, which can be minimized if the driver is driving it better, or if we get a MOSFET with lower gate capacitance. We're going to have a better controller and a better MOSFET, so hopefully less than 5 watts. So, you know, average power 5 watts there. And, control click is plot. Click was delete trace. and then there's 52 watts on the load. So yeah. Oh wait, 52. So 90% efficient on my first attempt. No complaints from me. No complaints from me. We can optimize this further, right? This was a first stab at a control system. This was not meant to be the final implementation of the design. So that's starting to lose my voice. Don't normally talk this much. Just, it's been a while since I got in front of the camera, and we're kind of finishing up the Plant Life Project series. We're kicking off this new one. I've been pretty busy doing things outside of this as well, so just wanted to take some time, have a chat, walk you through what I've been working on, because I'm excited to share it with you, but it's not time to share it yet, so just kind of a glimpse into a few of the things I've been working on without a real in-depth explanation. So, talk to you soon. Talk to you real soon. Got a video coming out Tuesday. Not sure which one it is. It makes it pretty hard to tease. Let me pull up my schedule. Oh, yeah, we got a great video on tolerance this week. Yeah, I'm really excited for that. This was one, I made a few videos just this last week or week before, and I thought they really turned out well. I edited them, and yeah, they were really good. Just really kept the density down, did some simulation with a slightly tweaked kind of format, and I think it's good. I've just been trying to evolve the format, keep it a little more engaging, where it's like right up front, it'll tell you what we're going to do, and then we'll do it, and then it'll kind of summarize it, where before it just kind of started rambling on from the first minute. So I just added a little blurb. Well, okay, this isn't on these four, but like a month from now, the videos you see will have a little blurb at the beginning, like a one sentence. Today we're going to take a look at this microcontroller, right? Today we're going to talk about this dev kit. Something like that. And it'll just be very straightforward, very upfront about what the rest of that video is going to be about. Well, cheers. Have a great rest of your Sunday. And I'll talk to you soon. Bye.